Now, the title of this video is a bit deceptive because you cannot actually observe a black hole from the outside. But if you could fly close to a black hole, you'd probably see something like this. A black sphere in the center, surrounded by an extremely bright accretion disk. However, this black sphere in the center is not the black hole itself. This is called the black hole's shadow, and deep within this shadow is something called the event horizon, a non-physical boundary that marks a point of no return. The shadow is an optical effect caused by the bending of light around the black hole. It is the event horizon that we're interested in measuring, a region of space where no light, or anything else for that matter, can escape. And if you could see past this shadow, the event horizon would also appear black. Now, what does this mean? If we draw a simple diagram of a black hole, it would look something like this. In the center, we have the black hole, the remnants of a supernova explosion, where the core of the exploding star weighed more than 3 solar masses. Anything less than 3 solar masses, or 3 times the mass of our Sun, and the core would not have formed a black hole. It might have turned into a neutron star, or a white dwarf, for example. In effect, black holes are remains of stars that have collapsed under their own gravitational force, and are represented by a singularity. Then we have the event horizon, which to us looks like a black sphere. This event horizon is at a distance of rs from the singularity, and we call this the Schwarzschild radius. So this radius is the closest distance photons of light can get to the black hole before they're no longer able to escape the extreme gravitational pull. So how can we calculate this Schwarzschild radius? Well, first, we need to understand this formula. This formula tells us the minimum speed an object must have, which we call the escape velocity, when it's at a distance of r away from the center of mass m. And this is the minimum speed the object requires to escape the gravitational influence of this mass. So if we have a rocket on the surface of Earth, in order for this rocket to escape and fly off into space, it would need a velocity of over 11 kilometers per second. And notice here that the rocket's mass has no effect on its escape velocity. The only things that matter is the Earth's mass and how far away this rocket is from the Earth's centre of mass. So what's this got to do with the Schwarzschild radius and black holes? At the event horizon of the black hole, your escape velocity would need to equal the speed of light. On the other hand, if we fall beyond the event horizon, our escape velocity would now need to exceed the speed of light. So any photons at the event horizon, or just beneath it, will never escape this event horizon. So with our formula above, we can now imagine we are a photon of light positioned exactly at the Schwarzschild radius. Our speed is always at c in a vacuum. M is now the mass of the black hole, and by rearranging this new equation, we can find how close we need to be to the black hole of mass m for our escape velocity to be at the speed of light. This is the size of the event horizon.